Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous session we were discussing performance metrics, and in particular we had created a cumulative lift curve or gains chart. So this was the chart that we had created in the previous lecture. So as you can see, on x-axis we have the number of cases. So cases are increasing from 0 records to 5 records on x-axis, then 10 records, and then 15, 20, and this fashion. So as the number of cases increasing, what is the performance of the selected model? In the y-axis we have cumulative actual class. So cumulative actual class being identified by the model as we increase the number of cases. Now the dotted line is the reference line, where we have the cumulative ones as would be identified using a random selection approach, which would mostly rely on the probability value of a particular record belonging to a particular class, right. So when we start when we have 0 observation, this particular reference line will start from 0 and 0, no records and no identification, no classification. As we move to all the records, that is 24 observation in this case, you would see in the data set we had 12 owners and 12 non-owners. So therefore the class of interest being owner, so number of records belonging to the owner class are 12. So the probability of a particular record belonging to owner class is 12 divided by 24, that is 0.5. So you would see that the last point coordinates being 24 and 12, and if you look at, so this being the reference line, so this being the average case. Now how our model is performing, you can see the cumulative actual class values and how this particular line in black color, the stepwise line in black color, is the performance of our model. As the number of cases increase, we can see the gap or separation between this reference line and the actual line is increasing. That means model starts to perform better in comparison to this random selection case. So as we move further, there are slight blips in between where we take these steps, and then again the performance improves, where we see the slight blips or horizontal lines. These are actually misclassification. So our model has misclassified a particular observation. So class of interest being class 1, and that is being represented in the y-axis. Therefore a class an observation has been identified probably as class 1, which was actually class 0, right. So if we had a model which would explain all the observations perfectly, so each record to its own class, then that model would actually be represented by red dotted line. So you would see this particular model as we move along, right. Now this particular data that we have plotted in cumulative lift curve or gains chart is actually reflecting the rank ordering as well. So you would see that all the by this red dotted model, the perfect model will represent will correctly classify all the classes belonging to owner class. You can see this particular point is 12 cases. So all the cases have been correctly identified, and then you would see the horizontal line, because now all the cases belonging to non-owner classes are being identified. So this particular model is will go in this particular fashion. Our model, there are going to be few misclassifications, so therefore our model will deviate from this particular red line. But if we compare with the reference line, there is much more better performance by the model. Now let us go back to our discussion. Now what we have discussed in cumulative lift curve or gains chart in a way helps us in determining how much improvement our model is providing. If we had not used any model at all, what was the case, which was represented by reference line, and the gains that the lift from that no model scenario, that lift that has been given by the model that we could see in this chart. Now, the same information that we just plotted, that we had seen and plotted through gains chart, can also be done through decile chart. Now, this is alternative plot to convey the same information as gains chart, right. So, let us open RStudio and will generate decile chart. So, before generating decile chart, we would need to create a few variables. For example, decile chart, as we will see that we create different deciles which are nothing but bars, which represent the cumulative number of cases in percentage terms, 10% of cases, and what was the bar size, then 20% of the cases and what was the bar size, and this all, and then 30% of the cases and the respective bar plot. So, in this fashion we plot for all the cases. So, that is all 100% cases. So, if we have gaps for 10%, 20%, 30%, so we will have 10 such bars. So, for each bar we would try to compare, each bar would reflect the same kind of information which was reflected by gains chart, the lift that is given by the model. So, we will see how we can generate this. So, as we saw in the gains chart, the comparison was with respect to reference line. So, in this case, on y axis we will have decile mean divided by global mean. So, for every decile or bar will create the mean for all those values, and that would be divided by the global mean. So, global mean here being this value, which is actually the number of cases belonging to actual class 1 divided by number of total total cases. So, this particular value will give us the number of, will give us the global mean, the average case. So, let us first create this variable decile cases. So, this is nothing but a variable which is representing the number of observations that are going to be there for each decile or each bar. So, first decile will show some stat or some show bar about 2 observation, then 5 observation, 7 observation, 10 observation, in this fashion. So, 2 observation actually representing 10% of the total observation, in this case 24. So, it has been rounded to 2, then 5, this has been this is 20% of the total observation, that is 48 rounded to 5 observation, and in this fashion for different number of observations, different deciles will have different number of observations. So, let us create few more variables so that we are able to compute this decile mean for each decile. Global mean has also been computed, as you can see that this value is 0.5. Now, let us also compute this particular counter, initialize this particular counter. Now, in this particular for loop, what we have is we are running a counter I for all the decile cases, that is in this particular case there are 10 such deciles. So, the loop is going to be run on 10 times, and you would see in the next second line in the for loop, decile mean for every decile is being computed, and you can see that cumulative actual class is is being divided by the counter value, and that giving us the decile mean for that particular, because the I will have actually the number of decile cases. So, for a particular bar the number of cases, so the cumulative actual class is being divided by the number of cases for that particular decile. So, we will have decile mean, and then decile value for is being computed by dividing the decile mean by global mean. So, let us execute this for loop. Now, we will have decile numbers. Now, we will create a bar plot, we will actually create this decile. So, let us compute this. You would see a decile chart has been generated. on the y-axis we have decile mean divided by global mean, and you would see that this particular, and on the x-axis we have decile. So first decile representing 10% of the cases, and these 10% of cases are actually from that ordering, rank ordering that we have done based on the estimated probability numbers. So these are the most probable ones coming first, then 10% most probable ones coming first. Just like the cumulative lift chart, there also the most probable ones were coming first. Similarly, second decile, most probable ones, 20% of such cases coming first, and then 30%, because as we talked about in a business scenario, in a business context, we would be interested in identifying for example, in a case of promotional offer, we would be interested in identifying the customers who are most likely to respond to a particular promotional offer. Therefore, most likely ones we would like to mail first. So these two particular charts that we talked about are actually indicating the performance of our model in that sense, in rank ordering sense. So you would see that lift for decile 1 is actually 2 in comparison to the average case. For 20 is for decile 2, that is for 20% cases, again similar number. For 3 also, decile number 3 also similar number. As we move towards right side of x-axis, we would see that decile value keeps on decreasing, because as we go along and try to classify more number of cases, the lift values goes down. The same thing was reflected in this particular gains chart that we had. If we compare from here the random case, this average case, and we see the separation, we would see as we move further from this point onwards, we would see both these lines are closing, right. The same thing is reflected in the decile chart as well. Okay, so let's go back to our discussion on performance metrics. So next particular concept that we are going to talk about is asymmetric misclassification cost. So we talked about that when we would require to change the cutoff value, we talked about different scenarios when we have a particular class of interest. Then another scenario being that when asymmetric classification costs are involved. What is this particular concept? So when misclassification error for a class of interest is more costly than for other class. So sometimes it might so happen then that if a particular class of interest, if there is some misclassification error, it is more costly. This generally happens in a business context. For example, misclassifying a customer as false positive who is actually likely to respond to the promotional offering. So for example, if we were able to make a promotional offer, and that if that offer was accepted by the customer and he purchases that particular item, then we might end up making some profit. So if we are not able to correctly identify or classify that particular customer as the responder of the offer, then we stand to lose that particular profit that we could have made. So this is opportunity cost of foregone sale. So if we are not able to correctly classify a responder, then we'll lose on this particular opportunity cost of foregone sale. If we are so this particular cost has to be compared with the cost of making an offer. If the particular customer is not a responder, then the cost of making an offer would be much lesser than the opportunity cost of foregone sale. So it is important for us to identify a particular class, the class of interest, because if we are not able to do so, we would that is going to cost us more. So in this particular scenario, the misclassification rate metric that is generally applicable is not appropriate. Reason being, there are different costs associated with misclassification of different classes. Other consideration that could be there, For example, it might not just be the opportunity cost of a gone sale versus the cost of making an offer. There are some cost of analyzing data also. For example, if we build a data mining model, that would require us to have the data set in the first place. It might be in the form of data warehouses, data marts, and then the finally data would be extracted for the analytical problem, and therefore we'll develop a classification model, a classifier, and that will help us identify. So all that is going to incur a cost. So we should be incorporating that cost as well. If through this model we identify a particular class 1 member, then we should be incorporating this cost as well. So we need to look at the actual net value impact per record. So if we are able to correctly identify with the help of our model, data mining model, then we have to incorporate the cost of analyzing data as well. So actual net value impact per record would be much better. So eventually our goal, when asymmetric misclassification costs are there, our goal would not be minimizing the overall error or maximizing the overall accuracy, rather it would be minimization of cost or maximization of profits. Now while we do this, how to improve actual classification by incorporating asymmetric misclassification cost, how that can be done. So we'll see that, but before let's go through an example. So let's open Excel file. To understand misclassification cost further, before we discuss how we can incorporate misclassification cost to improve our modeling. So let's say we have this example, we have 1000 observations. This is our sample size, and 1% of this particular sample, they belong to the buyers category. So that would be 10 buyers, and then remaining would be non-buyers. So buyers would be 10 and remaining would be non-buyers. So if we use the naive classifier, if we don't build a data mining model, then what we will do following a naive classifier is assign all the cases to the majority class. So for example, in this case we look at the sample, then there are 10 buyers. So all those buyers would also be classified as non-buyers. That would lead to 1% error. So we will have 99% accuracy or 1% error. That seems to be a good model, but this is of no practical use. Reason being that we are not able to make any money out of it, because all the customers have been classified as non-buyers. So the opportunity cost for this particular model, the naive classifier, is going to be 100 rupees, given that profit from one buyer is 10 rupees and cost of sending the offer is 1 rupees. So if you look at, I have already written the formulas here. So you can see here that the numbers of buyers multiplied by the profit from one buyer that could be there, that gives us the opportunity cost numbers, that is 100 rupees. So this is the cost if we follow the naive classifier. Let's say we had a data mining model, and using this particular model we generated this classification matrix. So this particular model correctly classified 970 class 0 as class 0 members, but 20 were misclassified. So 20 of class 0 members were misclassified as class 1. 2 class 1 members were misclassified as class 0, and 8 class 1 members were correctly classified as class 1 members. So that gives us in terms of misclassification, 2 buyers has been misclassified as non-buyers, and 20 non-buyers have been misclassified as buyers. So that gives us an error of 2.2%. You can look at this particular value. You can see here that diagonal values, off diagonal values, and divided by all the observation, that gives us the error, that is 2.2%. If we compare this particular scenario with the name classifier, the error is on the higher side. But if we look at the classification matrix, now we are able to identify correctly 8 buyers. So that will give us some profit. So how we can understand that? So one way is to create a matrix of profit. So here we'll look at, depending on the results of classification model, how we can make profit from that. So because we were able to identify 28 members as belonging to class 1. So therefore from these, but only 8 of them were correctly classified as 1. So from these 8 members, will have 80 rupees, 10 from each buyer, and 20 which were which were classified as class 1, but they are actually class 0 members. So we will have 1 rupee cost of sending the offer, that is the cost, that is minus reflected through minus sign, minus 20. So overall we will have a profit of 60 rupees. So this is from the profit perspective. We can look at the same situation from the cost perspective. So cost of sending the offer is 1 rupee, and then the profit from one buyer is 10. So we look at the number of customers who have been incorrectly, number of class 1 customers who have been incorrectly classified as class 0. So these are there are 2 such customers, and profit that we could have made from them is 10. So this is 20. Now other members which have been classified as 1, 20 misclassified, and 8 correctly classified. So 20 and 8 is the value. So we look at from the cost perspective, total cost is going to be 48. Now we can either maximize this particular figure. We can either maximize, so our new goal would be maximization of this profit or minimization of this cost. So let's go back to our slides. Now as we talked about that, the actual classification would not be improved by what we discussed just now, whether by minimization of cost or maximization of profits through these new goals. So how do we improve actual classification? One way is change the rules of classification. For example, in the previous lectures we were talking about changing the cutoff value from 0.5. We can either increase or decrease, so that could be done. So that is one example. So what we can do here is we can create a new performance metric, so which is actually the average misclassification cost. So here we can look at this particular value CI, which is the cost of misclassifying a class I observation. So in this case we have 2 classes. So C0 is the cost of misclassifying a class 0 observation, and C1 is the cost of misclassifying a class 1 observation. So average misclassification cost, this new metric can be computed using C0 into N01, that is number of observation belonging to class 0 classified as misclassified as 1, then plus cost of misclassifying a class 1 observation, that is C1, into number of observation belonging to class 1 misclassified as 0. So this is misclassification. All the misclassification and the misclassification cost have been computed in the numerator divided by the total number of observation. So we can actually look to minimize this average misclassification cost. So that is how we can actually incorporate. So this could be our change. This could be new matrix where we can look to minimize this average misclassification cost, and thereby changing our classification rules and improve the classifications. Now for this we would have to estimate C0 and C1 values, right? So but if we look at this particular formula, if we divide, if we take C1 outside of this we will have a ratio C0 divided by C1. So other term would actually be the constant value. So therefore if we don't need to find out the actual cost of misclassification C0 C1. If there are more than 2 classes, this could be a costly process. So we don't need to do that if we are able to find out, if we are able to understand the ratio of these costs. That means how much more in comparison to a particular class, how much more costly it is going to be misclassify the members of other class. So we have the ratio of, if we are able to understand the ratio of, find out the ratio of these two numbers, that would suffice us to minimize this particular quantity or expression. Now sometimes the samples that we use for building our training partition might have one particular probabilities, but the new data on which we are going to apply our model might not have the same proportion of same proportion of records belonging to different class members. So the incorporation of prior probabilities can further improve the model. So in such cases, when we incorporate prior probability, our average misclassification cost, this particular formula will also change, but even in that case also the formula would change and it will become C0 multiplied by the probability value P0 N01 plus C1 P1 multiplied by N10. So we can again take the we don't need to again we can take the prior probabilities even in this case and incorporate that in our model. So we won't have to again find out the actual values, and even in that case the constant term can be separated, and we just have to know the ratio of these values. So that is why you would see that many softwares they would actually, many statistical software, they would actually ask you to specify the ratio of misclassification, ratio of cost, misclassification cost belonging to different observation, belonging to different class observation, belonging to different classes, and they also incorporate the prior probabilities. So let's go back to our Excel sheet, and the same information is being conveyed over here. The average misclassification cost of misclassifying a class 0 observation, that we need to incorporate, cost of misclassifying a class 1 observation, that we need to incorporate, and you would see that if it is cost is Q0 Q1 and prior probability is P0 P1, and we will have to change our sampling routine. So earlier if we just do the simple random sampling, that might not work in case of prior probabilities, because if there is a rare case, we will have to do oversampling for that particular case. So for that we use stratified sampling. So in such cases we will have to minimize not just this Q1 Q0, or we will also have to minimize this probability of a particular record belonging to class 0, and ratio of probability of class 0 membership, and probability of class 1 membership. So depending on the case, right, we can minimize the particular quantity. So we'll stop our discussion here, and we'll discuss further asymmetric misclassification cost and some other concept under performance matrix. Thank you.